That's coming up. There we go. All right. So Wednesday we did a couple of examples on Wednesday, but today we're going to do more examples, and then I'm gonna break y'all out. Once we get everybody here, I'm gonna break y'all out so we can work through uh, the rest of this handout. All right. So let's take that first example where it says uh, give the correct reagents to convert the given start materials into products. All right. And then it says determine the type of substitution mechanism. And it says to draw a reaction energy diagram for A and for C. All right. So let's start with A. Um, let's start with A. Let me turn this ringtone down. All right. And what do you think? Give the correct reagent. So how are we going to convert the alcohol on the left? How are we going to convert that into the alkyl halide on the right? Which method would you use?
Would you use PB R3?
Okay, so you could, but it's not the optimal reagent for tertiary alcohols. There's a reagent that we talked about that's better for tertiary alcohols than PBr3. Because PBr3 is better suited for primary and secondary. That's a good answer though.
Okay, thank you.
Mm-hmm. So what other reagents do we know about? We can't use thionyl chloride, right? Because that's specific for primary and secondary too. Am I right?
Yes. So would it be BH? Wait, no.
We only got 3 sets of reagents that we've discussed for turning alcohols into alkyl halides.
MBS?
Mm-mm. We haven't discussed that for this reaction though. All right, we've said that you can use HX or PBr3. Sorry about that, it's getting cut off. Or thionyl chloride, right? PBr3 is primary and secondary alcohols. This is primary and secondary.
I'm sorry, yes. Because the MBS will only be for allylic bromination, right?
Right.
Because it's radical mechanism.
Right.
Okay.
Right. So these are our 3 methods. That's what we have to choose from for each one of these reactions. So if HX is specific for tertiary alcohols, then that's what we got to use, right? Because this is a tertiary alcohol. So we would use, in this case, HBr.
Could you explain why it's a tertiary alcohol again? I don't really understand.
So this is the substitution pattern. This would be a primary. It's only bonded to 1 carbon. This would be a secondary. Because that carbon where the alcohol is bonded to 2 carbons. And then a tertiary would be here where the carbonyl carbon is bonded to 3 carbons.
Thank you so much.
Mm-hmm. All right. So for tertiary alcohol, you have to use HX, right? Whether it be HCl, HBr, HI, doesn't matter. All right. the second part of that question says, what type of substitution takes place? Right?
SN2.
Okay, we got a problem. If it's a tertiary substrate, which is what this is, can you do a SN2 substitution on a tertiary substrate? We talked about this on Wednesday.
No,
No.
I guess not.
You can't do SN2 on a tertiary substrate. Can somebody tell me why? I mean, I could scroll back up in the notes, but I want to see what somebody else can tell me. Anybody? All right, we talked about this Wednesday. So for SM2, right, it's concerted, and the nucleophile is going to come in from the opposite side of where your leaving group is. SM1, well, if the substrate is too crowded, then you can't do SN2, right? You have to go through a carbocation intermediate, which this reaction, if you remember the mechanism, does go through a carbocation intermediate. All right, let me cut it out, and we can talk about that mechanism. Put a page in right quick. All right, so if you have this alcohol, let me change colors. What's the first step in that mechanism? Anybody remember?
The OH and the H.
It's proton transfer, isn't it?
Yes.
So you take the proton from HBr, and then the oxygen here is what's picking that up. All right. What do I get from that?
You would get in intermediate,
Mm-hmm.
carbocation intermediate. It'd be water.
Yes. So the OH is now going to be converted into a hydronium, right?
Right.
That's that. And then what happens?
And then the bromine comes in and attacks.
It's actually, it doesn't attack yet. You lose water first.
Okay.
Right? And then you get a carbocation. And that's what the bromine is going to attack. Right? So here's bromine now coming in, and it's negative, and boom, it's attacking here. So that's going to give me the product. I'm not going to draw it out because we already saw it. Right? So you go through this carbocation, which is always indicative of SM1. class, bruh. Sorry. Right? So when we look at these reactions, we have to think about that, right? So this is not going to be a SN2, it's going to be a SN1, right? Because it's going to go through that carbocation intermediate. All right, let's do B. But we'll come back to the energy diagrams. But let's do B. What do you think? How would you convert that?
Wouldn't you use SOCO2 for this
Okay,
one?
good, yes. So you'll use thionyl chloride. Let me just rewrite that. Right? And that's going to convert that alcohol into that the chloride and the product. All right. Is that going to be SN2 or SN1?
SN2.
Good.
M2.
It's going to be SN2, right? Even when we discussed this, let me go back and refresh you, because when we discussed these mechanisms, we talked about the fact that they were either SN2 type or SN1 type. So right here, when we talked about the HX, we said it was a SN1 type mechanism. When we talked about the thionyl chloride mechanism, we said it was SN2 type. It's in there somewhere. Yeah, right here. So it's an SN2 type. And then for the PBr3, we also said that that was SN2 type. All right, so the thionyl chloride reaction is SN2. And then what else gives that away? Let me see if you were paying attention at the end of class the other day. What else gives it away that is SN2?
It's on the secondary alcohol.
Yeah, that's one clue. But look at what happens to the stereochemistry.
It switches. It's
Yes. Remember yesterday, well not yesterday, Wednesday we talked about that with an SN2 type mechanism, chiral centers get inverted. Right? If the reaction is happening at a chiral center, it's going to get inverted. It's going to get switched in the product because of how the reaction happens. So when we go back to here, you can see it. You can see the OH is wedged, and then in the product, the chlorine is on a dash. Might be hard to see. Let me see if I can do something. Make the dash a little bit more visible. That's even worse. Right? So the chlorine is on a dash, and then the OH is on the wedge. So that's another clue that it's SN2. Right? You always get this inversion of stereochemistry. All right. What about the next reaction?
Yeah, I'm having a hard time understanding this one, but I think it's PBr3.
Okay. I agree with that. That you could use PBr3. That's a couple of things that give it away. But yeah, first of all, you convert it into a bromide, so you need a reagent that's going to turn your alcohol into a bromide. And then what about the other? What else do you see in that reaction? And when I say that, I mean, what type of substitution is it?
So would it be SN2 because of the stereochemistry switch?
Yes. Right, you can see that this is on a wedge. I'm sorry, on a dash. And then that this here is on a wedge now. So we know that that's a SN2 type substitution.
Dr. Russell, why do they invert, like change?
Because of how the nucleophile attacks. So like in
Okay.
the SN2, it's concerted. And so the nucleophile comes in as the leaving group is leaving, but it doesn't come in from the same side of the leaving group. It's got to come from the opposite side.
Okay, thank you.
So let me show you. I can put an example down here. Right. So if you have a carbon, and it's got a leaving group attached to it, right? And let's just put hydrogens here. Then your nucleophile, let's say you have a bromine coming in. It's going to come from this side, right? If the bromine comes from the same side as the leaving group, what do you think is going to happen? There's a term for that we learn, or a phrase. It has to do with the size of the groups and them bumping into one another and touching one another.
Is it steric interference?
Yes, steric interference. If the bromine comes from this side and tries to attack from here, I'm gonna put a red X here. So when you see this in the notes later, you'll know that it can't happen. Right? If it tries to attack from the same side as the leaving group, you're gonna encounter steric interference, and the energy for that pathway is gonna be way increased, like by a lot.
Okay, right.
Now let me write this the right way. So it can attack from the same side of the leaving group. Right, so that steric interference it plays a huge role in a lot of different things. That, like, what you'll find out if you study organic past part 2, is that all your reactions are dictated by either sterics or electronics. Like, it's either going to be some type of electronic effect, orbital overlap, electron density type of argument, or it's going to be a steric argument.
Okay, because I was thinking about this morning, like in a practical lab sense. How do you? Because I'm trying to picture how scientists like come up with these different methods. Like, how do they know what to choose, or is there like a certain protocol that they already follow, or are they like looking at rejogging their memory from like college to see what reactions to use, or like?
Well, you have to think about it, right? Science is like an ocean. You know what I mean? Mm-hmm. It's a huge body of work. So a lot of stuff has already been studied.
Right.
That's how you kind of know, like, first of all, you got a toolbox, like I was saying the other day, full of reactions. And all those different reactions that have already been done, you can say, hey, I need to make this. So let me try this method. And if that doesn't work, then I'll try this method. But you try to do it in as efficient of a manner as possible. You know what I mean? So, but
Right,
it's
right.
a lot of stuff has already been studied. A lot of the mechanistic work has already been done. Like
Okay.
for the
Okay.
SN2 and the SN1 stuff, that there's boatloads of research that's been done on that. That's how
Okay.
we know so much about it.
Mm-hmm.
Yeah.
Okay. Okay. That makes sense.
hmm And so then what happens is if you're developing a method, like if you are a graduate student or you have a lab, you're a PI on a big grant and you got a lab, you're in a lab, what you do is in method development is you test different parameters. Like you look at what the change in size of a substituent, how that affects the outcome of a reaction. You look at how
Okay.
the solvent affects it. You look at how if I put an electron withdrawing group on there, how that affects it. Or if I put a
Mm-hmm.
donating group, how that that's called optimization. Like you go through
Okay.
these reaction optimization protocols if you're trying to develop a method too. And then once you publish it, everybody can
Mm-hmm.
see it.
Okay. Okay. That's
That's why
cool.
you
Okay,
have,
that makes sense. Yeah.
yeah, that's why you have like journals, people publish their
Mm-hmm.
work. And
Mm-hmm.
that's why when you publish, you got to tell the truth.
Right.
Yeah. So you don't have people all jammed up thinking that, they can do something that they really can't.
Right. Right.
So yeah, that's a great question. That's a
Thank you.
yeah, great question. All right. I'm gonna let y'all go in these breakout rooms for a minute. I want y'all to finish these last two problems, and then we're gonna finish the backside of this. I want you to do the last two problems, D and E, and I want you to do the two problems here and when out in the breakout rooms. And then what I want you to do also, the bonus question we're gonna do together. That's how I'm feeling real benevolent today because I already worked out. I already have my little shake. I'm drinking my tea, feeling real woosah. So we're gonna do the bonus together. Um, so yeah.
Dr. Ruff, the
hmm
other two you said D and E, and which other two? The two after that?
The two on the back page. Do you have the handout?
Yes, I'm looking
Yeah,
at it.
yeah. So D and E on the front page, and then the first two questions on the back page.
Okay, thank you.
Mm-hmm. So I'm gonna stop sharing, and let me see. I need to make
I'm
these.
sorry, Dr. Russell.
Yes.
So with the SN2,
Mm-hmm.
you can tell those it's a SN2 because it's a secondary alcohol, the stereochemistry switches, and the chiral centers invert. Is that all?
Well, that's the the chiral center inverting and the stereochemistry switching is the same thing. So, but there are other parameters. We're just not talking about them right now. Like the solvent can help you to tell whether it's SN1 or SN2. Uh, the type of substrate, the leaving group, all of that. But right now we're just looking at the stereochemistry and the substrate type, secondary, primary, so on and so forth.
Okay.
Yeah, we're gonna talk more about this when we get to the section on substitution. We're gonna talk a lot about it actually. All right, so I'm gonna make these breakout rooms right quick. I'll give y'all about 10 minutes in there, and we're gonna come back and discuss what you did. And just like last time, one person from each group, or we can just, I don't know how to do that because it's so many groups and so few problems. We'll figure it out. But I'm gonna break y'all out into breakout rooms so you can work on those last two questions and then work on the two questions on the back page. So hopefully everybody has this handout. How many people we got? 37. I'm gonna do 6 rooms. 37. I'm gonna do 6. There'll be 6 people in each room. All right. So I'm gonna create that and open them. Boom. And everybody should have gotten an invitation to join a breakout room. So go ahead and do that. We're gonna do those. I want you to do those last two questions on the front page, D and E, and then on the back page, I want you to do the first two questions. Don't touch the bonus yet. We're gonna work on that together. right. If you're still in the main room, you need to join whichever breakout room you got assigned to. Is it the hydrogen? So what are we looking at? We're asking about the carbocation, right? The plus charge on carbon. How do we rank those? What's the criteria for stability? Like how do we know what's a stable carbocation and what's an unstable carbocation? What determines that?
Is
You're
it
right.
out of
They
that?
are already in order. You're right. But there's a reason why tertiary carbocation, which is the one on the far left, is more stable than a secondary or a primary.
It's because of the position.
The position of what?
Would it be because it's able to spread out the charge more than the other ones? Or
It's not necessarily spread. It does have something to do with the charge, and I think by position, whoever that was, I didn't see who it was, but where the
Does
charge
it,
is matters. But it's
Does it
not.
have to do? Oh, sorry.
Go ahead.
Does it have to do anything with how many carbons like it's connected to?
Yes,
that's
that's
what I
the
was
key.
getting to with the position part.
Yeah. I kind of figured that's what you meant. But yes, it has to do with how many carbons are attached to the carbon that's positively charged. The more carbons that are around it, the more stable it's going to be, because all of those carbons are contributing. Let me jog your memory. Some electron density towards that plus charge. Do y'all remember that? Like those arrows look terrible. Hold up. There's a dipole in the direction of that plus charge for each one of those carbons that's attached. And so because of that, it's more stable, because each one of those carbon-carbon bonds is donating electron density towards that carbon that's right here. Right. So it's the groups around it that help to stabilize it by giving it electron density. There's a term that if you didn't, well, it's called hyperconjugation. Right. That's the term for how carbon bonds stabilize positive charges. They donate electron density towards that plus charge. So you can imagine, as you take carbons away from that carbon that has the plus charge on it, then the stability is going to decrease. That's why the secondary is less stable. And then the primary is even less stable. And then the methyl is the least stable of all of them. The one on the very end that I had covered up and didn't see. Right? That's the worst of all because it has no carbons around it to help stabilize it. All right. What what about the next question? And how would you go ahead?
I have a gander at it. I don't know if it's right, but I took a shot at it.
Okay.
Okay.
Yeah. Are you gonna write it in or? Oh, you okay? Gotcha. I see you now. Okay. I agree. I agree with that. I agree with that. So, what would you get in that box? Like, what would that intermediate look like? Okay. 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 Good. Good. I agree with that 100%. So that's what the alcohol would look like when it's protonated. And then you put the other arrow in to show it leaving. Is that what that is? Okay, good. So what would the carbo
Yeah.
say again?
I was trying to say yes, but I couldn't click on it.
That's okay. Yeah, but that's right. I agree. I had to slide the screen over some. So the carbocation would end up on this carbon right here. So if you in that last box, you would just draw that carbon without the OH group on it with a plus charge. That's good. Good work. All right, so down here, this is the carbocation would just look like this with a plus charge right there. Got to zoom on it. All right, good. So you have an arrow coming from here to here. Right, and then in here you'll have that hydronium. All right. We're not gonna have time to do the bonus question, but I wanted to do this question with you. But
Wait,
what I'll
Dr. Russell,
do,
can you go up a little bit before you go to the next question?
say that again.
Can you go up a
Go over the one we just did.
I'm good, Dr. Russell.
Mm-hmm. Yeah, it's just so I showed the arrow for the proton transfer, which gave you the hydronium, the protonated alcohol in the middle, and then I didn't put that arrow in. The arrow for the loss of leaving group, which should come from here, right? Like that. And that's how you get your carbocation. Let me pull that down so I can put it in the box. So that's how you get that. All right. So we out of time. I can't do the bonus with you. But let me
We got time.
Are you sure about that?
Yeah, for the ones who don't, I mean,
Yeah.
is it going to be recorded?
Mm-hmm. It
Yeah.
is recorded.
Post a recording for them.
You want them bonus points. All right.
I was gonna ask if you could post the bonus question.
Yeah, I'm so let's do this. Let's do this real quick. Let's go through the arrow pushing. And because I got another class after this too, but I can be a few minutes late. What's the first step in that mechanism? So let's do that. We're gonna work it together.
Is it to put an arrow from the oxygen to the hydrogen?
Yes. Here to here. Like that.
Yes.
Okay, what do we get from that?
Hydronium, and then the chlorine would be positive.
Chlorine.
No, negative. Sorry,
Yeah.
negative.
That's okay. So we're gonna have this like that. I'll draw the oxygen in a second. I just needed to zoom in so I can get my lines looking straight. So here, that's positive, right? And then what happens after that? After you make the hydronium, what's the whole purpose of making it into a hydronium ion?
So you can get a
You can
carbon.
release it.
Leaving, make it a better leaving group. So I'm gonna do this, boom, like that, and then that's gonna be here. right. Now let me draw the product in, and then let me see if we can figure out why we got that product that we did. So I'm gonna draw the product in first, and then we're gonna backtrack and think about how it happened. Come on, pen. So this is the product. But it's not the expected product, is it?
No, but why?
I think I get it.
What happened? What do you what does it look like happened? Let me do this.
It looks like the chlorine went to the most stable, where it'd be most stable, because I think like we said, like for the cation to be more stable, it would be the one where it's connected to the most carbon. I don't know.
Yeah, but that carbon is not free in the intermediate, is it?
No.
There's a way to make it free though. Anybody want to take a stab at that? We learned this in part 1. Well, if you took it from me, we talked about it. So something has to happen. Like when you have a secondary carbon next to a tertiary carbon, a lot of times what happens is the carbocation will rearrange to give you the tertiary carbocation. So this methyl shift is a type of rearrangement. Man, I hate running out of room. It's a type of rearrangement. So this group right here can shift over. So this is a CH3. I can pick that up and move it to here. Right? The whole group and the pair of electrons that's in the bond. And so what that's going to give me is a different carbocation. It'll give me a tertiary carbocation where the plus charge is here now. And then that CH3 will be here. Like that. It's called a methyl shift. Right? Anybody remember that when if you took that part 1 from me, we talked about rearrangements. Anybody remember that? Probably not. All right, but this is what the chlorine is going to attack. Like that. That's how we get that product. So I'm going to write that over here. So if a secondary, oh, I'm going to run out of room for that. I'll write it in before I post the notes. But if you have a secondary carbocation that's adjacent to a tertiary carbon, sometimes you'll see this type of rearrangement. And then now the plus charge is on the tertiary carbon, which is more stable. Somebody said that earlier. And that's what chlorine is going to attack. All right. Any questions about that? Ooh,
Dr. Russell, you said if a secondary carbocation is adjacent to a primary
a tertiary carbon, then
okay.
Then you can see. Then sometimes you'll see this type of rearrangement.
Okay.
Dr. Russell, for the mechanism, will we have to draw the carbocation rearranging, or you just write it's a methyl shift? And
well, it's best to show it. If you ask to show it, it's best to show it, because that's the only way you can explain the product.
Okay, and by showing it, will we just have to write like what you wrote, whether the CL is grabbing that or is attacking to that carbocation, or would you have to actually draw the cation shifting each time?
Well, it depends on the problem, right? Because it's a special case. It happens when you have a secondary carbocation or some less stable carbocation adjacent to a tertiary carbon. So it's not going to happen all the time. It only happens in specific cases. And this happens to be one of those cases. All right, I gotta log out now and go to my next
Dr.
class.
Russell, quick question.
Go ahead.
Is the exam due Sunday or today?
No, Sunday.
Okay.
Yeah, Sunday at 11:59. But I'm not gonna be able to open it right this second because I gotta start this next class.
Oh, take your time. Have a good day.
All right, thank you, Dr. Russell.
All
Dr.
right.
Russell,
Yes,
are the worksheets due Sunday too?
yes. You turn everything in Sunday when you do the exam, or after you finish the exam, or before you start it, whenever you want to turn it in.
Okay, thank
But
you.
it will be due on Sunday. All right. Everybody good? All right. Stop share.